very basic configuration of BGP for IPv4. Let's go a little bit deeper here. We've got a more complex topology on the screen, and for time reasons, I've already configured BGP everywhere except on router R3. So let's configure router R3 to advertise its attached internal network and to form neighborships with routers R2, ISP1, and ISP2. Now note that we might not want R3 to advertise the networks connecting to ISP1 or ISP2, because if we did, we might inadvertently become a transit area for internet traffic going from one ISP through us to the other ISP. We don't want that. Let's get started on router R3 by going into global configuration mode, and let's create our BGP routing process by saying router BGP, and we'll give an autonomous system number of 65001. And I want to give this BGP a router ID. That's going to make it easier to recognize as we're looking at show commands. And based on the topology you see on screen, I'm going to give it a router ID of 3.3.3.3. We'll say BGP router-ID 3.3.3.3. And keep in mind, just like OSPF, when we set the router ID to a number like this, we're not saying that this network is reachable via us. This is simply an ID, which happens to look like an IPv4 address. So BGP router-ID 3.3.3.3. Now let's point to each of our three neighbors. We'll say neighbor, and router R2 has an IP address of 10.1.1.2. And when we say the remote autonomous system is 65,001, that might seem like a mistake because that autonomous system is not remote. That's our autonomous system. We're part of 65,001. So is that okay? It is. What we're doing is forming an iBGP connection, an interior BGP connection, as opposed to an exterior BGP connection. So this is called iBGP. When we connect to another autonomous system, that's an eBGP session. And notice we already have that adjacency that came up. Great news. Let's say neighbor and give the IP address of the ISP1 router. That's 198.51.100.2. It's in a remote autonomous system of 65,002. And let's point over to ISP2. We'll say neighbor 198.51.100.6. Notice we've got an adjacency now with ISP1. Great. But for ISP2, it's in remote autonomous system 65,004. And we should see that adjacency come up in just a moment. Now, what network do I want to advertise to my neighbors? The only network I really want to advertise is the 10.1.1.0 network, the network between R2 and R3 with a 24-bit subnet mask. I'll say network 10.1.1.0, and it's going to have a mask of 255.255.255.0. And we're done with our configuration on router R3. Now let's verify this BGP configuration. Let's see what routes that BGP knows how to reach. And let's identify the preferred routes and autonomous system paths. Let's do a show IP BGP. And let's take a look at our output. I have a loopback interface on the iNet router, and that's what we're pretending is a network out on the internet. So if I can get to the 5.5.5.0/24 network, I'm getting to what we're calling the internet here in this lab environment. And notice there are two ways to get there. I could get there via ISP1, or I could get there via ISP2. Notice the greater than sign here. This greater than sign means that this is the preferred route. Notice here it says this is the best path. Even though I've got two paths, it's going to be pointing to ISP1. Now, I mentioned earlier in an earlier video that BGP does not pay any attention whatsoever to bandwidth. But if we look at the bandwidth, there's only 10 meg of bandwidth between R3 and ISP1. There's 100 meg of bandwidth between R3 and ISP2. We're going over the slower link. That's not optimal. We'll deal with that in just a few moments. But first, let's see if we can interpret some more of this output. We see the next top IP addresses. This is ISP2's router. This is ISP1. And we see that to get to our destination network of 5.5.5.0/24, I'm going to be going through 65,004. That's where ISP2 lives. Then I'll be going into the autonomous system of 65,003. That's where the iNet router lives. And then the I says that we're going to use an IGP, an interior gateway protocol, within that autonomous system because our IGP, an interior gateway protocol within that autonomous system because our network lives within this last autonomous system right here. Now, something that's a bit confusing in this output, there are two codes that read I. Notice that there is a status code of I, meaning internal, and there's an origin code of I, meaning IGP. Which one is this? You might want to make a note of this. This I as part of the path refers to the origin code. We're going to get to that network via an IGP once we get into this autonomous system. Now this I for internal, where does that show up? Here's the network of 10.1.1.0/24. That's inside of our autonomous system. So we can see that to reach that network, it's going to be internal to our autonomous system. And notice the R code over here that we see showing up from time to time. What does the R code mean? Well, it sounds really bad. It says that an R is a RIB failure. That's a routing information-based failure. That means that BGP was unsuccessful in trying to install this route that's known to BGP. It was not successful in injecting it into the router's IP routing table. Now, this could be for a perfectly valid reason. For example, the route is known via another routing source that's more believable in terms of administrative distance. In this case, the networks that are marked with an R, if you notice, they're directly connected to R3. And a connected route has an administrative distance of 0. That's why these routes that are known to BGP could not be installed in the router's IP routing table. Let's take a look at our BGP neighbors by doing a show IP BGP summary command. And we see that our router identifier that we hard-coded is 3.3.3.3. We can see the IP addresses of all of our neighbors. And we can see the autonomous system in which each neighbor resides. And if we want very detailed information about our neighbors, we could do a show IP BGP neighbors command. I rarely do this one, but it gives us detailed information. For example, this neighbor, which is router R2 in our case, there's its IP address, so there's its autonomous system. We see its router ID, and we see that our state is established, meaning we've established that TCP session with our neighbor. Now, let's see if router R3 has reachability to this generic internet address, which is the loopback IP address on the internet router, and that's 5.5.5.5. So let's do a ping to 5.5.5.5. Is that successful? Yes, it is. Awesome. Now let's see if router R2 has learned about all the routes in the network. Let's go to router R2 and let's do a show IP BGP. Now I'm taking a quick look here and I think I see all the networks in our topology table, in this BGP table. But let's once again see if we can get to this generic internet address of 5.5.5.5. We see an entry for that network right here. Question is, can I ping it? Can I ping 5.5.5.5? No. That is failing. Why is it failing? Well, we know that we have a route in our BGP topology table for 5.5.5.5, but let's see if we made it into the routing table. Let's do a show IP route. Does the IP routing table know how to get to the 5.5.5.5 IP address? No, it doesn't. What could be going on here? That's curious. In fact, you might want to pause the video and think about it for a moment. There's a clue on screen right now that should indicate to you why we're unable to get to that network. You might want to pause the video and come back when you think you figured it out. All right. Did you notice that in our BGP table, to get to the 5.5.5.0/24 network, we went to a next hop of 198.51.100.2, which, by the way, is the ISP1 router. The challenge is, if we look at our IP routing table, we don't know how to get to that next hop. And if we don't know how to get to the next hop, we're not going to inject a BGP route into the IP routing table, and that makes sense. We wouldn't be able to reach it anyway. Now, the reason we're having this symptom is a characteristic of iBGP. With iBGP, where we're talking to a neighbor within our own autonomous system, when one router sends a route advertisement to another router, by default, it does not change the next hop address. So router R3 said, okay, to get to 5.5.5.0/24, I've got a next hop IP address of 198.51.100.2. And it left that as the next hop IP address as we advertised it to R2. The good news is there's a way to fix that. We can use the next hop self option when router R3 is pointing to its neighbor of R2. So when he routes R3 advertised to R2, they're going to be marked in such a way that router R3 is the next hop to reach those networks. Here's what we can do. Let's go back to router R3. Let's go into global configuration mode and back into router configuration mode for BGP Autonomous System 65001. And let's say neighbor, and we'll point to R2 as our neighbor with an IP address of 10.1.1.2. And we're going to use this option of next-hop-self. And we'll press enter. Now, just to speed things up a little bit, I'm going to say clear IP BGP star so that we'll relearn our routes and I'll re-advertise the networks down to R2. And we'll see if router R2 now knows how to get to 5.5.5.5 because R3 should have said, oh yeah, if you want to get to that network, I'm your next hop. Come to me. And R2 obviously knows how to get to R3 because it's on the same link. The next hop should be showing up as 10.1.1.1. Now, even after the adjacencies come up, it takes a little bit of time for everything to be relearned. It may not have happened yet. Let's try. Let's do a show IP BGP and see if we have the 5.5.5.0 network in our BGP topology table. Not yet. Let's give it a few more moments. We'll try again. And let's try one more time. Yeah, it's going to take several seconds. I'll tell you what I'll do, just so you don't have to wait through this on the video. I'm going to pause the video, and given enough time, this advertisement should happen, and we'll come back in about a minute or two, and we'll see if we have that listed then. All right, I just gave the show IP BGP command again, and look at this. Now we've got this network of 5.5.5.0/24 with a next hop of 10.1.1.1. Awesome, that's router R3. Can I now ping 5.5.5.5? Let's try. Ping 5.5.5.5. And now that is successful. Now let's continue with the verification by shifting our attention over to router R1. Let's see what it knows about. On router R1, let's do a show IP BGP. And it does not know about much. It can only see networks inside of this autonomous system. Can you guess what might be going on? Again, you might want to pause the video and think about what could be happening here. All right, well, here's a rule that BGP has. A BGP router says, if I learn a route from another router in my autonomous system, I'm not going to advertise it to any other neighbors in my autonomous system. So in this case, R2 learned a route from R3 in its autonomous system, and it says, I'm not going to advertise it to any other neighbors in this autonomous system. In other words, I'm not going to advertise it to router R1. Now, an easy way to fix this would be to make R1 and R3 neighbors. We could have a full mesh of adjacencies. And that might be fine for this example, but in a really large network, that just doesn't scale well. What we could do instead is to configure something called a route reflector. And in this example, we're going to have all routers within Autonomous System 65001 form a neighborship with R2, and they already have that neighborship. Then we're going to say, R2, you are a route reflector. Now, here's what a route reflector does. When it learns a route from an iBGP neighbor, it's going to advertise that route out to all of its other iBGP neighbors. And the configuration is all done on R2. So let's go into R2, and we'll go into router configuration mode for BGP Autonomous System 65001. And we're going to say, for the neighbor of 172.16.1.1, which is R1, we're going to say, you're going to be a route reflector client. And for the neighbor at 10.1.1.1, you're also going to be a route reflector client. Now, if we go to R1, it should have learned about all the routes on the network and be able to reach the quote-unquote internet. So let's go over to router R1. Let's once again do a show IP BGP. It knows about 5.5.5.0/24. It thinks the next hop is R3. Let's do a show IP route. Does it know how to get to the 10.1.1.0 network? It seems to. Let's try this. Let's do a ping to 5.5.5.5. Excellent. Now everybody in our autonomous system can get out to the internet. Our autonomous system can get out to the internet. But let's now optimize and tweak our configuration a bit. Now in this example, we've got a fairly small topology, but imagine we had dozens and dozens of routers that were interconnected. They're all running BGP. If we started applying a bunch of policies, like how we're doing route summarization or how we're filtering routes, and we did that to every single neighbor on a router that had lots of neighbors, that router's CPU could take a serious hit. However, in many cases, we might have a route that is peering with multiple neighbors, and it wants to apply the same policy to all of those neighbors. So here's what we can do. Instead of doing that one-by-one configuration, one neighbor and then another neighbor, what we can do is configure something called a peer group. And configuring peer groups will not only reduce our configuration burden, it's also going to help reduce the CPU load on the router. Now in this example, let's say that router R3 wants to make sure that it's not receiving advertisements for private IP addresses, in other words, RFC 1918 addresses. We don't want to receive those addresses from one of its ISPs. And we could do that through the use of a prefix list, which we apply to the neighbor. But to illustrate the configuration of peer groups, let's apply that prefix list not to each neighbor individually. Let's apply it to the peer group containing both routers ISP1 and ISP2. And just for time's sake, I've already created the prefix list. That's a bit off topic from this particular video, so we won't get into all the syntax. Let me just give you a brief look at it. On R3, I could say show IP prefix -list, and we see that we've got these sequence numbers that are denying these RFC 1918 addresses, and I'm permitting everything else. Now on router R3, let's define a peer group. Let's apply this prefix list in the incoming direction because we don't want to learn those private IP addresses from our ISPs. We want to apply that prefix list to the peer group. And finally, we'll tell each of our neighbors that they belong to this peer group. Here's how we do that. Let's go into router configuration mode for BGP Autonomous System 65001. And I'm going to say neighbor BGP-PG for peer group. And I'm going to say that this is a peer group. And now I'm going to apply this BGP demo prefix list, not to a specific neighbor, but to a peer group. I'm going to say neighbor, and I'm going to say the peer group name instead of a specific neighbor. That's BGP-PG. I'm going to apply the prefix list of BGP-demo in the incoming direction. Now I need to say who belongs to this peer group. And it's both of my neighbors, specifically the two ISP neighbors. I'll say 198.51.100.2 peer group BGP-PG. That's for ISP1. Now let's do the same thing for ISP2. All right. Now, when we're filtering incoming routes, any routes that should not be permitted to come in, we don't have to do it individually on each neighbor. We just do it once for the entire peer group because our ISP routers belong to the same peer group. Now, before moving on, I want to get rid of the peer group that we've created here because in our upcoming video, it's not going to be compatible with what we want to do then. In our next video, we're going to take a look at how we can treat our ISPs very differently instead of the same, how we can prefer to go over that 100 meg link both for incoming and outgoing traffic. So for now, let's say no neighbor BGP-PG peer group. To delete that peer group, now I need to reestablish my neighborships with my ISPs. I'll say neighbor 198.51.100.2 remote AS 65002. That's for ISP1. Now for ISP2, we'll point to its IP address, and it's in Autonomous System 65004. And that should bring up both of our neighborships. Let's end the video here, and I'm going to end it by doing the clear IP BGP star again. It's going to make everything be relearned. And then in our next video, we want to see if we can influence that path selection, because Remember, we were using the 10 meg link instead of the 100 meg link to get out to the internet. And the bad news is it was the same in the other direction. And we want to fix that in our next video.